Hello. Welcome everyone. Hope you're well and you're having a nice afternoon. And thanks for joining me today. Please let me know if I've got any problems with my sharing screen. You can see my screen or not. And yeah, I'm going to make a start. So today's webinar is about machine learning with Python. My name is Aida and I am a junior data scientist at Jumping Rivers. For those who don't know Jumping Rivers, we are a consultancy company, data science consultancy company, and we work in different projects with regards to data science with different industries like pharma, finance, and the public sector. And among other things, we do also training, which is delivering training courses in R, Python, SQL, machine learning, and so on, from the very beginners to more advanced levels as well. And so we do have a dedicated team for dashboard development and deployment. Yeah, basically this is us. And we also have host some events as well. We are going to host next year in June AI in production, and we have got 1 day of workshops and then the main day of the talks. And for those who have been in touch with us in the previous years, this has been like Shiny Production, so it was more Shiny focused conference. But next year's conference is going to be more dedicated to the AI topic. And so we have got a special offer for those who have attended 2 webinars with us. You could have a 30% discount. And we also host the Northeast Data Science Meetup, which is a local group meetup. And we have got tonight actually an event at 6 p.m. Where my colleague Miles will be discussing the use of LLMs with R and Python. Additionally, we have got the Leeds Data Science Meetup, which is going to happen next Tuesday. And then with regards to the webinars in December, on the 11th of December, my colleague Oshin is going to talk about accessible Shiny. Can everyone see my screen? And yes, sure. I've got a, thank you. Now the microphone is somehow better. Thank you. Thanks for letting me know. Great. So yeah, today's tutorial is going to be a discussion, a general discussion, a presentation from my side. And anytime you can drop a question in the Q&A section here in Zoom. And additionally, we are going to have a 10-minute discussion at the end of this meeting. So yeah, if you have got any questions, we can discuss. And then we can meet again in December for another topic. So yeah, today I decided to talk about tree-based methods within the wide range of machine learning methods that are available there for us to use. I decided to talk a little bit more about these methods because I feel like they are widely implemented and used, but actually people don't talk very much about the the mathematics behind these methods, and we have to kind of like make sure that a certain method is defined a certain way in order to understand the model output as well. So in this workshop, I'm going to talk about tree-based methods with application in regression problems and also classification problems. So we use a regression tree method when we are trying to model a continuous outcome variable. And we use a classification tree method when we are trying to model a categorical outcome. So as we would do in a more like in a complete like traditional modeling techniques, right? I've got regression for linear regression, like modeling a continuous variable, and I've got logistic regression, for example, for modeling a categorical outcome variable. And so we are going to go through regression trees, classification trees, which are the basics within the tree-based methods. And we are going to build upon the knowledge on these two methods to understand further what random forests are and gradient boosted techniques as well. And then I'll end this presentation with some conclusion on how the traditional regression methods work against the tree-based methods that we are going to review throughout this presentation, this tutorial. So just to give you a kind of like a general overview of tree-based methods is that tree-based methods are algorithmic methods which involve stratifying and segmentation of the predictor space, right, into some subregions by using the mean, right, or when I'm performing a regression tree, or the mode when I'm performing some classification type of problem. So I use the mean for the response variable in the case of regression tree, and then the mode for a classification tree. So basically, we are going to go into depth with both of these methods, and we are going to see some examples, some illustrations in Python as well. Just to be consistent, I have been using scikit-learn package throughout these illustrations because I think it's quite a powerful package for performing machine learning and in Python. So just to give some like a broad overview of statistical modeling, because statistical modeling I think is a more traditional type of approach when it comes to data modeling. So the problem is that we have got some data and we are interested to kind of model a response variable y, which could be a continuous or a categorical type of variable, as a function of some predictors, right? I've got p predictors in the other side. So I assume that hopefully there is some relationship between this set of variables, the predictor space and the response variable. And I'm going to summarize this as a function, right? So I'm going to build a mapping between the y, the response variable, and the set of variables that are my independent variables. And I include some error term because this mapping is not so perfect to match everything. So I have to allow myself to have this error term. Then we have got some assumptions on that error term and so on. So this is the idea when we perform a regression modeling technique. And yeah, we are interested on the estimation of this function f, which could be a linear type of estimation. So the relationship between the x variables and the y variables could be linear. If it is not linear, then you can approach the problem of applying some polynomial type of regression or like logistic regression and so on. Today, we are going to have a look at the regression trees, which is a method used when my response variable is a continuous response. So it's a continuous variable. And the idea behind the process, right, the algorithm is that I do build some subregions in the feature space. So let's say in X, right, if I've got a single variable X, for example, I divide this feature space in some subregions in such a way that these regions are non-overlapping, right? I've got maybe K distinct regions that I say that are R1, R2, Rk. And then for each observation that falls in the region Rk, we calculate the mean of the response values from the training observations within Rk. So I basically have got, right, the average mean within each region, right, which is this y Rk in here. which I can derive from like the split of the predictor space into subregions. And then I have got the observations itself, right? I have got the Y observations from the observed data that I have got. And so I'm interested to kind of like build this a split of the predictor space in such a way that I do minimize this measure here, right? So my observed data in Y is as close as possible to these averages that I obtain from each region, right? And so this is like an optimization problem, right? I'm going to choose those regions in such a way that this metric here is minimized, is as small as possible. And yeah, and then the tree itself, right? Because we are going to obtain a tree as a result, is that I start by the total amount of the observed data. I do a binary split, and then for each of that split, I try to optimize this metric here, right? And we are going to have an example on how these things work. So for the illustration, I decided to use a patient-level data from a scikit-learn package. So it's a data set publicly available, basically, which is called diabetes dataset. And it has got a set of variables. So my response variable Y is a quantitative measure of disease progression 1 year after the baseline. So this is the variable that I'm trying to model. And then as independent variables, I've got age of the patient, sex, BMI, blood pressure, and other metrics from blood, right? And so I'm interested to see which of these basically variables affect my response variable, right? And so yeah, to implement this, as I mentioned, I'm going to use the scikit-learn package. From scikit-learn package, I import this method here, which is train test split, which basically helps us to kind of divide the entire data set that I have got, the entire data set that I have got into subsets. One of them is the training set, and then the other one is the testing set. We do this because we want to keep in one side this testing set to kind of evaluate the performance of our model later on after fitting our model. And so this is a very, broadly used technique for assessing model performance in machine learning. And then I import also the decision tree regressor function to kind of like be able to fit the regression tree in the data. And last, I have got the diabetes data set, which is going to be used for modeling the for illustration of this method, basically. And so, yeah, I load the data set, and then I do split the data set in training and test, right? With a ratio of 80% and 20%. And then I'm going to focus for now in just one variable, because I wanted to kind of like illustrate how a regression tree works and how it's visualized, right? Because just like it's so simple and easy to understand the procedure behind the algorithm, right? So just to illustrate this, I wanted to check the regression tree using the blood pressure, which is this variable here, against the disease progression, which is my response variable, right? So yeah, I extract the blood pressure column, and then I fit a tree. I fit the tree using the decision tree regressor. And then I build this object, this model object, where I've got the fitted model. And I basically decide that in this tree I should use 3 nodes, and we are going to visualize that immediately by just plotting the tree basically. And then for fitting the model, I call the fit function, and then I feed the variables of interest that I'm interested to model, right? So the training blood pressure and the response variable, which is the disease progression, right? And so once I've got the model, the object that has been fitted and so on, I'm able to use the output of this model to visualize the tree, right? How the method has performed into this data. So yeah, from the scikit-learn package, I import the tree class, and then I use the pyplot from the matplot library to kind of visualize the plot as well. So yeah, I make a plot of the tree by just using plot underscore tree, and then I obtain this output here, right? So I'm dividing my predictor space, which is blood pressure, against the disease progression, which is the continuous outcome variable that I have got. So as I mentioned earlier, the tree is built in such a way that for each split there is 2 possible directions. So it's a binary tree, right? So because I'm interested to minimize this measure here, so I want to kind of produce 2 regions, which the mean outcome within each region is as close as possible to my response variable, right? So at each step, at each node, that metric of the metric of residual sum of squares has been calculated and optimized for that threshold, right, for that node. And so yeah, the blood pressure variable has been standardized, and then the algorithm has optimized all these nodes. Like the first split has been at level 0.24, and then the next has been minus 0.26, and so on. And so we have got here, right, the level where the split has happened, right, but also the metric, the residual, like the residual sum of squares that we perform at each step, right? And then also the number of samples, so the number of observations that I have got within each region, basically. And so the mean value that is associated for that region as well. So it's very easy and nice to visualize how things change from one region to another, right? And how these nodes has been optimized to satisfy, to minimize this residual sum of squares. Now, this is just for illustration purposes, right? Because I just wanted to show how the tree is fitted and how it looks like, right? But in a real world example is that we don't have just one single variable to be fitted into the tree. We have got a set of variables which build the predictor space. And on the other side, I have got the response variable, which is a continuous variable. And so this is what I'm going to do now. So we are going to use again the diabetes data set, right? But in this case, I'm going to use all this set of variables that we saw above here, like age, sex, BMI, and so on, and build a tree, right? Build a tree using all these predictor variables, and then the y variable is the same as we used above. So it's a multivariate case, basically. And so if I run this model, I will have the model output, right? And then what we can do with the model output is to check, right, to assess the performance of the model. And before I mentioned that we tend to split the observed data into a test and training, right? So I can keep this test data to kind of assess the performance of my model. And so I basically use my model, right, to predict over those um, points, right, where I haven't got the observations, right, and then right the y predicted, right, and then I'm interested to compare these predictions that I have got from the model to the observed ones that I have got from my data set, my real data set that I have got. And so I measure some mean squared error and root mean squared error and mean absolute error. So all these metrics can tell us somehow how is our model performing. And so for now, I have got 86, right, which is like the unit of the outcome variable. And the mean absolute error is somehow smaller because it's calculated differently, right? So I cannot tell right now how good my model is, right? I need to perform some other model to kind of like compare these metrics of performance, right? And we are going to do that later by using a random forest rather than just a regression tree. And we are going to discuss the limitations that the regression and classification trees have and why we need to use more advanced methods rather than just these simple techniques, right? And so, yeah, I was going to talk a little bit about classification trees, which is fitted when my y variable is a categorical variable, right? So for a regression tree, we consider the mean of the response variable within that region, right? And we were trying to kind of like minimize this difference between the observed values on the y variable minus the mean within that region, right? In this case, in a categorical classification setting, it's not possible because we have got classes among the y variables. So instead of using the mean of the observations in y, we use basically we predict that each observation belongs to the most commonly occurring class for the training observations in the regions to which it belongs, right? So we are going to consider the class that has got the highest frequency. And so instead of using residual sum of squares, we are going to use some other metric, which is called Gini index. And it's given like this mathematical expression here. And in practice, what Gini index gives us is a homogeneity within each region, basically. And it's a measure of purity. And small value of the Gini index indicates that that region contains observations from a single class. And so, yeah, we are going to illustrate this method, right, with a data set which is contained again in the scikit-learn package. And it is it's some collection of data from some chemical analysis of wines, which is grown in some region in Italy, but there is 3 types of wines. So yeah, my predictor space is just some metrics about the analysis of these wines. And then the y variable is a variable which shows us these 3 different types of wine, like the 3 different cultivators within the same region, right, where the grape has grown. And so, yeah, the idea is that we want to check, right, which of these variables here has got a major effect on the wine type, right? The wine type that has got 3 classes, basically. And so, yeah, we import the data as we did for the diabetes data set, and then we split the data in training and test by a 0.2, 0.8 ratio. And then to kind of fit the decision tree classifier, the classification tree, we use this basically this function here, which is decision tree classifier, which also this has been contained within a scikit-learn package, and then we fit the model. Now, for assessing the performance of the model, a common way is to build a confusion matrix. And yeah, basically a confusion matrix is giving us how many times we have predicted the right thing, right? So how many times we have predicted that a type of wine two, for example, has fallen in the right classification. And so this lower diagonal here and the upper diagonal is showing us the number of times that we have done the wrong prediction, right? In this case, our model, like our model that we have fitted, the classifier model, has worked quite well. So we have got a good behavior of the model. So the diagonal here shows how many times we have predicted the right thing. And then I've got zeros below here. So it's good behavior of like the model is behaving quite well. Now someone asked is if I can share the Jupyter notebooks to follow. Yeah, I could share. I could make a public repo, and you can just clone that repo and like set up in your machine this code to run. And yeah, definitely. And then how do you decide to use root mean squared error or mean absolute error? So this is no preference if I use the one or the other. Both of metrics are kind of like showing us how far away we are from the observed data. So basically what I'm trying to check is that um, like from the predictions that I have made from the model, how far away I have fallen compared to the observed data. So both of them are giving us the same information, essentially. It's just the way that they are calculated is slightly different. That's why we obtain different values. But I think, yeah, both of them are giving the same information. They are not comparable, right? Because uh, the way that they have been calculated, right? So yeah, we are going to have a look at later on how we can um, use these metrics to compare with other methods and to check if the model somehow has performed better within another method. But they are not comparable in this stage, right? And yeah, so basically, basically like for a classification type of problem, I could yeah just like display this confusion matrix, and it's giving us a good amount of information how many times we have predicted the right thing, basically the right class. Yeah, and then I wanted to discuss a little bit more advanced type of techniques because of the limitation that you know, like classification tree and regression tree have. So basically, both of the methods tend to overfit the data, which means that they have got a high variance. And when we introduce a slightly different data to the same model, it might behave completely differently, right? So a way to kind of address this issue is by simulating more samples from the observed data. And this can be done by a procedure called bootstrap, right? Bootstrap is quite well-known technique in statistics, and it is used to kind of like generate samples from the observed data and use this sample to make some estimate of interest, and then rather than just having a point estimate, I have got you know, an interval like many of them, so I can kind of like give um, an idea of how the range of the values that that point estimate could have, rather than just a single point estimate. And the same idea is followed also in this tree-based method setting, because instead of fitting this a single tree into observed data, I can actually build many samples by using Bootstrap, and then on all these Bootstrap samples, I can fit a tree, right? A regression or a classification tree. And then as a result, as an output, I can produce just an average set, like an average tree among those trees, right? So this way, the performance of the models improve quite a bit. And the idea of bugging then is used also in random forests. So basically, um, yeah, random forests work like the bootstrapping within the bugging techniques, but with a small change that they decorrelate the trees. So basically, when we perform a decision tree, all predictor variables are considered, and the cut point, right, for building for separating regions is chosen by minimizing the RSS or maybe the Gini index for a classification type of problem. But when we perform a random forest, we actually don't use the entire set of the variables, but we use this square root of p. So we give the chance to all the variables, which might not be very important for the model, to be included in the model. So we obtain trees which have got a higher variability, and when we average among them, we have got a better, extracting a better information. So yeah, basically. We have got like the way of like fitting these models in Python is very easy. I can just import the random forest regressor from the scikit-learn package, and then in the same way as we fitted a regression tree, right? We can use the split that we obtained from the original data in training and test, and then I can fit the model into this data, right? But this time using the random forest, right? And so I can make predictions, as we mentioned, and then we can kind of like extract some metrics of performance of the model. So if I like make the same procedure that we did earlier, like calculating the mean squared error, then absolute error, mean absolute error, the performance of our model actually has improved quite a bit. So mean squared error in this case by fitting a random forest is 59. And if I go above, it was much higher when just fitting a single regression tree, right? And the same happens with the mean absolute error, which it has got the value of 65 in here, and then down here has got like 49. So yeah, we can see just with a simple example how much the behavior have improved, the behavior of the model have improved. Now, with regards to the model assessment and things, there is other methods to check the model assessment, to check the model performance. Sorry, and basically you could implement the cross validation, which is like leaving a set, out of your training data, and then repeat this process of train test split many times. Basically, that is the idea. So you can kind of like have a better idea of like capture more features from the data, not just a single split. That is the main idea. And then I was going to talk a little bit about boosting methods, which are also these are widely used in practice, and lots of people use them when it comes to fit tree-based methods in real world and big data, usually. And yeah, basically the idea behind boosting is that the trees are growing sequentially, and each tree is growing by using the information from a previous tree. So basically, instead of fitting the tree in the training data, the method actually uses the residual term rather than the observed data, and then the residual term then is used on the updated for each step of the tree. Now, boosting methods are a little bit more complex, and they would require quite a bit of discussion around them. But yeah, someone could go on and read about them maybe in your own time. But yeah, the boosting algorithm is controlled by 3 parameters, which are the tuning parameters essentially, which is the number of trees, right? The number of trees that you want to include in the search, right? The shrinkage parameter and the number of nodes in each tree. So how big the tree is going to be, essentially. Also those have been proved to have a much more better performance in terms of accuracy, prediction accuracy, compared to the regression or classification trees. Note that boosting methods and also random forests work with a classification type of problem, but also regression, like when my outcome variable is continuous. And so you could call a random forest classifier in the case of like fitting a classification type of random forest classification type of problem, right? And yeah, what we do afterwards. So after we feed the model, we have got the tree. We can read the tree, of course, as we did in this stage in here. This was a very simple example. If you try to do this in the real world, when you have got many variables included in the model and so on, the tree is very messy, so it's very hard to read. But yeah, one thing that we can do is to basically extract information that we have from each variable, right? And say which of these variables, which I've included from the predictor space, is going to be the most important feature. So it's something called feature importance, essentially, and showing us how much important each of the variables has been for our model. Or in other words, it is basically how much a given variable has contributed on decreasing, right, this RSS, right? How much has been the total amount of RSS or Gini index has decreased due to the splits of a certain predictor. But in practice, is saying how much important and how much close that variable is to my response variable. And so, yeah, we can visualize actually, or you could just like, extract these values from the model output. And you basically can also display a bar plot like this just to visualize which of the variables has been important for your model. And in this case, we are using the diabetes data set, and one of the variables that seems to be highly important for my disease progression is S5, which we're going to have a look in a second. And BMI and blood pressure and other things. Age doesn't seem so much significant, and neither does sex. So this S5 is the variable that has been relevant to my model. And if I go to have a look, it is a type of fat which has been found in the blood. So that probably, if we talk to a doctor, it's going to say that metric probably influences the disease progression on diabetes. I had a high relevance for the BMI, which you expect, blood pressure, which you expect. So the model somehow is detecting those features that are quite important for disease progression in diabetes. And so, yeah, I was going to very briefly discuss a little bit about traditional regression methods and also tree-based methods. I would say that when we have got a small size of data, probably a more traditional technique is better to be implemented, because these algorithms that we have just described probably don't have enough data to learn from and to give us good predictions. But if we have got a big size of data, probably like regression or classification trees are very, very easy to be implemented and understood. They are robust when the data contain outliers. And plotting a tree, for example, is quite easy. They handle very well qualitative predictor variables. And as I said, probably in a small data size, we go for a regression method. And when we fit a complex tree like a random forest or like a gradient boosting method, probably it's better to kind of just like visualize the output in terms of like feature importance, right? Which gives us some insight for you know um, seeing which of the variables are important. And so uh, yeah, basically um, the idea is that like these methods suffer again from like the uh, collinearity of the independent variables and so on, so it's things to take into account as well. And yeah, this is what I had prepared for you. And somebody has asked, is RSS residual sum of squares? RSS is this metric that we have defined in here, basically. So it is the discrepancy between the observed values in the target variable, right, minus the average of the target variable within each region, right? So yeah, basically that is the way that the RSS has been defined. Um, Somebody asks if there is an automated fashion to fit models using various variables and choose which best performance characteristics. I'm not sure about that. So it's probably worth to manually experiment a little bit with the models and just like extract maybe a good idea could be kind of like set up a range of values for hyperparameters and then explore all those and output the model metric, performance metric, and just choose those ones that have been lower ones maybe. um, the recording, I think the recording is going to be published on YouTube, so definitely it's going to be available soon. And then for the Jupyter notebook, I'll make sure that I'll create a public repo in the Jumping Rivers GitHub page. So you can basically clone that repo and then yeah, follow the code from there. Yeah, definitely it could be possible. Yeah, definitely. Like if you use like a simple decision tree classifier, it's going to give you better idea of like just assessing and maybe visualizing the trees and so on. So it's better to start from there and then start like going to a random forest classifier. I hope I didn't miss any of the questions. But yeah, thanks everyone for joining me. Yeah, I'll make sure that I'll create a public repo soon so you can follow the code. Thanks a lot. See you soon. Next webinar is going to be 11th of December. Thank you.